Let's take a look at the squeeze theorem, sometimes called the sandwich theorem. We'll look at the formal statement and then match it up with the graph. Suppose that f of x is less than or equal to g of x is less than or equal to h of x. So g of x is squeezed or sandwiched in between two other functions for all x in some open interval containing a, except possibly at a itself. So there could be a hole at a. And the limit as x approaches a of f of x equals the limit as x approaches a of h of x. So those two outside functions, they have the same limit as x approaches a. They have the limit L. Well then, the limit as x approaches a of g of x, that inside squeezed in function, must also equal L. So again, let's match it up with this graph over here, a representative graph to understand the concept. So here we have this function g of x. We really want to know what is the limit as x approaches a of g of x, but it's a hard function, right? When I look at it, I don't know what basic function that is. So what I can do though, let's say, is squeeze it between two other nicer functions. Let's say f of x and h of x, and these look nicer. They look kind of like parabolas. If we can show that the limit as x approaches a of f of x and h of x have the same limit value L, and g of x is sandwiched between those two, then it must also have the same limit value L. Now let's go ahead and apply it to some examples. Suppose f of x is a function such that x cubed minus 3 is less than or equal to f of x, and that's less than or equal to 3x squared minus 7 for all x in the interval from open 1 to 3. Use the squeeze theorem to find the limit as x approaches 2 of f of x. So we're interested in the limit as x approaches 2 of that squeezed in function f of x. We already have this inequality built for us. And we know that this is true on the interval from 1 to 3, and we're trying to evaluate as x approaches 2, which is in that interval. So it works out nicely. So the squeeze theorem says that as long as the limit of the two outer functions is the same value, the limit of the inner function will be that value. So let's go ahead and take the limit of those two outer functions. So here I've taken the original inequality we were given, put the limit as x approaches 2 in front of all of them, and the limit on the left side is found by doing direct substitution. So 2 cubed is 8 minus 3 is 5. So the limit on the left is 5. And then on the right, 3 times 2 squared, that's 12 minus 7 is also 5. So what we then know is that the limit as x approaches 2 of f of x is trapped between 5 and 5. So the only value it can possibly be by the squeeze theorem is 5. So we would want to formally state that when we apply the squeeze theorem, we are writing up a little bit of a proof. And this one was a bit easier because the original inequality was already provided, but in other examples, we're going to have to come up with that inequality. Let's find the limit as x approaches 0 of x squared times sine of 1 over x using the squeeze theorem. This is a classic squeeze theorem problem. And so we need to build an inequality where this function is trapped between two other nicer functions that we can evaluate. So when our function involves sine or cosine, we want to start with the fact that we know that the sine function in general is trapped between -1 and 1. That is the range of the sine function. So here we know that -1 is less than or equal to sine of 1 over x is less than or equal to 1. So here, the only place this is not defined is 0, but that's okay because the squeeze theorem says as long as I'm defined on an open interval around 0, but possibly not including 0. So that's fine. So anything else that I substitute in here, I know the outputs of sine are trapped between -1 and 1. But I want that inside function to be x squared times sine of 1 over x. So what I'm going to do is multiply each part of this 3-part inequality by x squared. And the inequality will still hold because I'm multiplying by a positive value. So x squared because I'm squaring it, is either 0 or always positive. So here I've gone ahead and multiplied each piece of the inequality by x squared, and now that middle piece is exactly the function inside my limit. So as long as the limit as x approaches 0 of the left function and the right function are the same value, that's going to force the limit of the middle function to be that same value by the squeeze theorem. So let's go ahead and take the limit of each piece. And so on the left side, the limit as x approaches 0 of negative x squared, by direct substitution, that's just 0. Same thing on the right-hand side, I'm just going to get 0. So it forces that limit in the middle, the one we were trying to evaluate, to also be 0. So that limit, if it must be greater than or equal to 0 and less than or equal to 0, well then it must just be 0. So we'll formally write our conclusion that this was by the squeeze theorem that we got this result. Before wrapping this up, I just want to go back to a point that I made very briefly, the idea that we were allowed to multiply each part of this by x squared and keep the inequality because x squared is positive. So if I take a minute and think about a basic numerical inequality, like 1 is less than or equal to 2 is less than or equal to 3, if I multiply by the same positive value, so multiply by 4, let's say, 4 is less than or equal to 8 is less than or equal to 12, that's still true. But if I were to multiply by a negative value, -1, -2, -3, so multiplying everything by -1, now the inequalities are going to flip. The greatest value is -1, and the smallest value is -3. So we have to be careful when we're dealing with inequalities if we multiply by the same thing to each piece. So here, x squared, again, was always positive. Other values you might multiply by are absolute value of x, because that's always positive. So just kind of things to keep in mind for other potential squeeze theorem problems.